Hi, I'm Stefan. Welcome to the TwoStack Developer channel. In today's episode, we'll be broadcasting our first transaction onto the Bitcoin network. We'll still only be using our locally installed Regression-Test-Mode Node. That's a mouthful, sorry. Local Regression-Test-Mode Node. Yeah. This is the node that we configured in the previous episode. So we'll be using that to broadcast the transaction onto. But before we can actually even get to broadcasting the transaction, we would need to compose the transaction. So we would need something to send. In order for that to happen, we would need to figure out what type of transaction we'll be sending. We'll be sending and for the purpose of today's episode, we'll send a simple payment transaction between two addresses. So we will need at least one Bitcoin address to receive funds that we control, and then a second Bitcoin address that we will be sending funds to. Both of these addresses need to be derived. The address derivation proceeds by first generating a private key, using that private key to derive a public key, using that public key to then derive an address. And this address we'll be using to send and receive coins on. Right? Let's get started. Okay, we're ready to start building our example application. Now, I'll be using Kotlin to actually write this application, and I've created generated a sample application using my IDE. And I'm using IntelliJ IDEA as my IDE. This, of course, use the IDE or the text editor that you're most familiar with. I happen to really like IntelliJ IDEA. You might prefer something else. The idea is this is a Gradle project, and as such, we will need to actually import and get the dependencies properly lined up before we actually start this JVM-based project. We do have a second library in the TwoStack toolkit, I guess you could call it, and that one is for Dart. But this video is going to focus on actually using Kotlin. Now, I should give a bit of a disclaimer here. I'm basically new to Kotlin. I've been programming in Kotlin for all of maybe 3 or 4 days, right? So please forgive me if I make some obvious weird errors as we go along. Now, I'm going to be using the Bitcoin4J Bitcoin library. The Bitcoin4J library is a library that I built over the past few weeks. It is now in Maven Central, and the first thing, of course, we will need to do is we need to resolve that dependency inside of our IDE. So why don't we head over to Maven Central, search for the repository, and get it from there, right? So the repository will show up, so it's in Central, right? So it will show up in either of these. So I can just search for TwoStack, and I'm on Maven repository right now. Here it shows up as Bitcoin4J. The latest version is 1.3. Please don't download any of the older versions. Get the latest version. The latest version fixes, especially fixes a bug with respect to transactions that really don't use the old versions. Use the newest version. So click on that, and we get through to Maven or Gradle dependencies that we can actually grab here. We can grab this one right here, which is essentially this would basically be a copy paste. Now this is of course the Groovy DSL. If you look at my project inside Kotlin, I'm actually using the Kotlin DSL for Gradle, which means that my my dependency will essentially look like this, which is that I need to bring in the dependency, which in my case will be org.toStack. The artifact ID will be Bitcoin4J, and the version is 1.3.0. And that should be it. And then I can basically go into the IDE and ask it to resolve those dependencies for Gradle. The Gradle build is proceeding now. Let me make this a little smaller. Come on, TikTok, let's go. Okay, so while that is happening, I don't want us to stare at the screen. Let's go over to me quickly showing you where this is actually located. So this is in GitHub under Bitcoin in the two-stack repository or the two-stack organization in GitHub under Bitcoin4J. You can find this, right? So it's right here. Let me make this a little bit larger. So you go to Bitcoin4J. The library is here. If you want access to the source code, if you want to fork the repo, you can come here to actually get that done. Also, if you find any bugs or issues with the Bitcoin4J library, please come and raise an issue inside GitHub. The library is fairly new, and as more and more people are going to be using it, either if you have suggestions or if you spot obvious bugs or problems with the library, please do give me a shout. Yeah. Right. I think that we are done with our with resolving our imports here. Let's quickly check that the external library actually shows up. Apologies for my tool window being a little bit small on the left hand side here. Let's quickly make sure that org 2stack4j Bitcoin. Yeah. Yep. So we're imported there, right? So we've got that imported now. I'm going to close that side window. So we only have our IDE windows open. I'm going to switch over now. The application that I actually generated, or rather the new project that I created inside IntelliJ was basically to generate a simple console application, and it essentially generated the Hello World application for me. I'm going to strip out this stuff because we don't need it. Now, if you remember from the introduction to this video, what I mentioned was in order for us to get to the point where we broadcast a transaction locally, the first thing that we actually need to do is to get a private key, derive a public key from that private key, then get an address from there. And I mentioned that we needed two sets of these. So two private keys, two public keys, and two addresses. The first address will basically be, we can call her Alice, and Alice will be sending some coins to Bob. So we'll have Alice's set of keys and Bob's set of keys. The first thing, of course, we do is we get those addresses, that infrastructure set up. There are two convenience functions in the Bitcoin4J library. They are private key, and I'm just going to use my IDE to help me resolve these. I'm going to say this is going to be Alice private key, and I will set this up in a second. And of course, then there's a private key for Bob, and I'm going to call that Bob private key. And this is Kotlin, so sorry. Forget the language that I'm in. So in Kotlin, of course, I need to the variable declarations in Kotlin works the other way around. I have to specify the variable name and then the type. Right. So how do we actually create the private keys? Well, we invoke the constructor, and then there is inside the two-stack library there is a elliptic curve key generator. The elliptic curve key generator, I'm going to import that from the two-stack library. You probably noticed that there is also an EC-key class inside Java, and also inside, probably inside Bouncy Castle there is one as well. The one we actually want to use is the one that's inside the Bitcoin4J library, right? So you'll notice here that the Bitcoin4J EC-key has been imported. Private key, private. I want to create a private key. And then we want to create a private key for Bob, and these will actually just generate random private keys. Now, the way that these keys are set right now, let me just, I hate if my indentation doesn't line up. The way that these are set up right now, this will generate 2 random private keys, which means that every time we run the application, we will actually get 2 random private keys. I don't want to do that. I don't want to go back and forth with the private key generation. So usually there is a bit of more ceremony that has to go into this, but for the sake of time, what I will do is I will dump the private keys to a text format, copy that, paste it back into the source code as comments, and then just use those private keys. So I'll run the application through once, get my private keys as text, and then reconstruct my private keys from the text that I've actually created, right? I will stop and start the video at random points so that I have sort of fixed chunks of video to work with in post-production. So if the video stops a little abruptly and then restarts at any point in time, just bear with me. I'm really new to this. Okay, so let's do that first. So we can actually get the width. Hang on. Ls private key dot get, not the public key. We want to just generate the width, which will, if we look at the signature here, it returns a string for us, right? So we want to print this to the console, and now I need to explain what this toWidth function actually does. Width is referred to, or width stands for wallet import format. The wallet import format is a standard that developed around Bitcoin addresses and the way in which we can easily have, or we can have a text-based representation of a destination to send our coins in a foolproof manner. The wallet import format is essentially a base 58 encoded string. Importantly though, this function takes a network type, so we need to specify a network type, and I'm going to specify testnet, which allows us to generate testnet addresses. This is a part of the wallet import formats structure, is that it basically prepends the address with a byte that basically points at whether or not, or discriminates between whether or not we're generating an address for the testnet or for the mainnet. The reason for this is obvious, right? You don't want to generate a testnet address and then end up providing this testnet address to somebody on mainnet, and you end up sending coins to an address that you either don't have keys for, or was a test address or whatever. So that confusion, right? You don't want to be losing your coins by sending money on the wrong network. So the best way, so basically that's what this is for. You specify the address, the network that we'll be using for this. I'm going to do the same for Bob's private key. I'm going to print it out to the console, and I'm going to run this through. Right. So I need to now make a note here that I'm actually running Alice first, and then I'm going to run Bob. Right. I'm just going to ignore the SLF4J warning there right now. So I've got 2 addresses now, which you can probably, I don't know if you can see that in the console, these 2 addresses. So this is Alice's address, and this is Bob's address. Right? These are the 2 addresses that have basically just been dumped out for me. Now, I'm going to delete this code, and then I'm going to comment out this code, and I'm going to recreate Alice's private key. And I'm going to, this time, I'm going to basically reconstruct her private key from the width text file that I've got. So I'm going to say, okay, create an immutable variable for Alice width, paste that in there. And then get this. Okay, let me close this over here. right? I've blown up the text substantially so that it's readable, but of course that means that these, okay, I'll just be explicit here that this is actually a string. Why is this moaning at me? Oh, because I've got Alice with defined twice. So Bob with the type inference should take care of this, right? So I can, and this is not Bob's with. Let me come on. Failing at typing. And the string is is case sensitive, so I want to be sure that I'm not actually messing it up. Otherwise, the import will fail. If the string also checksums, right? So it's case sensitive and it checksums, which means that it will fail hard if it's so Bob private key is a private key, and I want to essentially use the factory constructor to retrieve it from, and look at this, me, right? What am I doing? Still in Java mode, still attaching semicolons where they're not needed. Now, I don't know if type inference will take care of this. It will. I'm going to leave it. I'm going to leave the explicit types in there just for the sake of this of the code. It makes the code more explicit because I'm actually basically doing a tutorial, right? Okay, so now we've done that. We can run this again, and it should run okay. Yeah. So it's not going to give us any output, but you know, now that I've got the keys imported, so first step of this is done. I've got the private keys imported, or rather the private keys created first, dumped them out to the console, and I've now recreated those private keys by reading them back from essentially from the text exported versions. Obviously, these private keys are sensitive. If you generate your own, eventually we'll be using other techniques to secure our private keys. This is not production code, and you should never use private keys like this. And the last thing you should do is generate private keys like this and then use them on the mainnet, or goodness, check them into GitHub or do something silly like that, right? These private keys are actually meant to be kept private. So for test purposes and on the testnet and just for the demo, I'll just use it this way because the idea is to get the point across about private keys, the exporting and the importing of them, right? Okay, so private keys are generated. We need to get public keys and then addresses from that. That's the first step. So get the public keys, get the addresses. Public keys are a little bit simpler. I can just go val ls pub becomes bob private dot get public key. Now for the public key generation here, come on, Stefan. So okay, sorry, I was basically calling a property. Anyway, so for and I am creating Bob's public key from, or Alice's public key from Bob's. So Bob pub from Bob's private key, and then get his public key, right? I'm just a bit confused here now. I did not recall that I actually created a property accessor on here, but okay, I'm going to assume, right? So here is why I said that I'm going to probably end up stumbling over some weirdness in Kotlin that I need to get used to. There is, I think, and I believe that when I wrote the Bitcoin4J library, that there is actually a get public key method in the library, right? So let's quickly go and look at the library code. Yes, so so here is the weirdness that I was talking about, right? Me getting used to Kotlin. So there is a get public key method inside the private key, but of course Kotlin prefers less ceremony than that. So it basically just gives me a property accessor. But when the code compiles, it of course delegates or actually generates the bytecode that fetches or invokes the get public key method on the private key class or object rather. Bear with me, folks. Bear with me. All right. So now I've got the public keys reconstructed. Okay, this needs to go under public keys. I'm going to get the addresses for, so Ellis address is going to be Ellis's, rather I'm just going to create an address from, let me import the address class. Come on, import this address class. And then the address class basically needs two things. Actually, I think I can create an address from a public key. Yeah, I'll just use this way. So the address, of course, has got a few constructors. You can reconstruct an address from a byte array, which is essentially the serialized version of an address, along with specifying the network type. Here, I now need to specify the network address type. No, that's wrong. I don't want main to be to sh. I want test pkh, public key hash, and the public key will be Ellis pub. Okay, and this is gonna need some explaining. Bob address is going to need to be created from Bob's public key. Okay, so now I've got these two addresses. Now you notice, for example, here, right, that I've now got two things here as part of all of this that I'm doing. When I created the private keys, I specified the network that the private keys were actually meant to be generated from, right? So if you recall, I did this, which was okay, let me just call this when I created the private key, and then when I essentially serialized this to the WIF format, I specified a network type, which can either be test, reg test, scaling test, or main. The test, reg test, and scaling test are all, for all intents and purposes, the actual address will be the address, the byte. I don't know what to call this thing, the discriminator byte on the front of the address that actually signals what network the address is meant to be used on. That byte is the same for test, reg test, and scaling test. It is used here, or these specific enumerated types to discriminate the networks are for convenience. So test, reg test, and scaling test all point to the same place, and main, of course, points to the main network. But the point that I was trying to get at was there is a network type here, which I used before, right, when I generated the WIF. And this network type, come on. What is wrong with my code? Maybe I just can't do two things at once. Maybe I just can't speak and type at the same time. Maybe that's the problem. All right, so as I was saying, there are network types and there are address types in the API. The network type refers to the network type. The network address type refers to the type of type of Bitcoin address that we are trying to generate for from the API. Now there are only two network address types. There is either a paid to script hash address type, or a pay to public key hash. Now, I didn't really want to create an enumerator type, which is test pk p2pkh. So I just called it test pkh, the public key hash, test public key hash address. Anyway, the reason why these things exist, and this brings me to the point that I actually want to talk about here, which is that this is what we refer to as a leaky abstraction, right? And I don't know if you don't know what a leaky abstraction is, please Google that. But the idea behind leaky abstraction is essentially there are some hidden parts of our infrastructure that ends up leaking into a different aspect of it. So in this case, there are things which are concerned with the consensus level protocol in Bitcoin, and there are things which are concerned with the user level stuff, wallets, addresses, etc. The bad, from a software developer's perspective, right? Bad practice is when your APIs end up leaking abstractions into parts of the code that you generally would prefer not for them to be. And the reason why I mentioned this particular leaky abstraction is because it is important to know about it, because it can bite you in the backside if you're not careful about it. The leaky abstraction here specifically is that we have on the BitcoinSV network, on the BitcoinSV network, we essentially have unbounded transaction types. So the concept of a transaction type does not exist on BitcoinSV anymore. The idea of a transaction type, or I should actually rephrase that. The idea of a transaction type does not exist at the consensus level, meaning what the miners will accept on BitcoinSV anymore. The miners on the BitcoinSV network will accept any validly signed transaction, right? Any transaction that spends a UTXO or is just valid in the consensus rules and it's got nothing to do with the shape of the transaction will be accepted. And this is a very important point. On the Bitcoin Cash and on the Bitcoin BTC networks, there are a limited number of types of transactions that are allowed to be sent onto the network. And the way in which the transaction types are constrained on these networks are that there are only very specific patterns of setting locking conditions and unlocking conditions for the script inside a transaction on those networks. I do realize that depending on your level of knowledge with the Bitcoin network, then I'm possibly using terms that you may or may not be familiar with. These will be clarified later, or if you really want to not wait until I have clarified in 2 or 3 episodes down the line what all of these different terms mean, you can go on to 2stack.org, read the documentation. You will basically get detailed explanations about the stuff that you may hear me say, but want to know what was that thing, okay? So, sorry, sidetrack. So leaky abstractions, right? And the reason why I mentioned this particular leaky abstraction is because historically now we have in Bitcoin this idea that there are constrained transaction types, and this idea of constrained transaction types still exists at the consensus layer on the Bitcoin BTC and the Bitcoin Cash networks. And that abstraction of constrained transaction types has leaked into the user space, where people have now built essentially wallet infrastructure that is constrained in the types of transactions that they will generate. Hence, in the APIs that we ended up building for things like constructing addresses that we can send to, we have injected this abstraction of constrained transaction types. And here we have constrained address types that have leaked in. The reason why it's important to know this is because BitcoinSV uses the same address format as that of the Bitcoin BTC network. So the two addresses, when you look at them, you will not be able to tell that one is a Bitcoin BTC address or one is a BitcoinSV address. Bitcoin Cash has a separate address format called cache address. And that is basically something that they did specifically to make themselves indistinguishable and to prevent folks from sending coins onto the wrong network. BitcoinSV has reverted the address format to the original Bitcoin address format, but we are now still burdened with this leaky abstraction of address types, network address types, which doesn't really exist as a real thing at the consensus layer. It's something that the wallets, and I'm really hoping that this little rant of mine kind of makes sense. And to recap then, in BitcoinSV, we don't have constrained transaction types at the network level. However, for the purpose of working with addresses, we still need to specify, if you're going to be using addresses to send and receive from, we still basically need to specify a transaction type, because the types of addresses and the types of transactions we'll be generating to send coins to and from these addresses will essentially have a particular shape when it comes to generating the locking and unlocking scripts. BitcoinSV does now have at least one new addressing protocol, and that is Paymail, which is a means of resolving a public key for a user, and then from that public key generating the locking conditions. But again, this is a little bit more advanced, and we'll get to these particular script or transaction types and how they're formatted and how they relate to public and private keys. One more thing that is really, really important to understand about addresses and how addresses factor into all of this on the network. Addresses are not actually, addresses never go onto the Bitcoin network. At the consensus level, these addresses that we generate here will never make it into the Bitcoin network. The addresses that we generate here are essentially a combination of taking the public key and creating a hash from it, and that hash is basically reformatted in a base 58 encoded format, so that when we give this address to somebody, the wallet can essentially get the hash of the public key out of this address and then generate a locking condition or send money using the hash of a public key. And it's that hash of the public key that is actually encoded at the network level into the transaction. The address itself is something that only exists in this format that we have here, only exists at the wallet level or at the application layer. Here the application layer is, of course, is the application that we are building. So from that long side track back to this, let me quickly print out. Failing to type again. Right. So I messed up here. Yes. I basically, when I flipped over to actually show you me printing the addresses onto the console, I forgot to switch the screens, so my face was all over the code, which of course nobody wants to see that. So I'm just quickly going to show you, right? This is just the last little bit here. I'm just going to print Alice address. The toString method has been overloaded to actually generate the base 58 encoded version of the actual addresses. I'm going to run the code. That should dump onto the console. You should see the two addresses generated here. And please remember that because we are reconstructing the private keys from essentially, we're reconstructing the private keys from the WIF, right? From the exported WIF that we have. That means that we are deterministically reconstructing the private keys. And because we are then deriving the public keys from those deterministically reconstructed private keys, It also means that we are, every time that we run this through, we are deterministically generating addresses. So there is a direct correlation between the width of the private key that we imported and the address that we would actually dump. So we can rerun the program over and over again. We'll get the same address over and over through subsequent runs, right? Okay, so to the code. This is going to be Ellis address string. This is going to be Bob's address string, and I'm gonna cut out the bit prior to this where I beg off recording anymore because I need to take a break here. My throat is basically, my voice is failing me. So when we come back from this break that I'm taking here now, we will do the next part, which is essentially trying to then send money or create the transaction. We'll start to construct the transaction that will eventually allow us to send money back and forth. But that is right after this break I'm taking now. Or as we say in South Africa, now.